we're not going to we're not going to bore you. Actually, we are. We're going to bore you with a lot of details. But before we get into the details, we'll talk a little bit high-level stuff, and then we'll get into the details. And let me introduce Craig Carlson. Craig Carlson is a legend in the storage industry. If you don't know him, you should get to know him better. I think he's part of every single board, SNIA board, NVMe board, T11, FCIA. So, he's got about 5 million miles. He's global services for life. And myself, I'm Rupen Mohan. I work for Hewlett-Packard. And fortunately or unfortunately, I've been around for quite a while too. And I was telling someone that I first worked on the Fibre Channel driver just, in 1996. MLX stock at that time was $1. I should have bought some more MLX stock at that time. Maybe I wouldn't be standing here, right? We were retired. All right. So this is the agenda, folks. We're going to talk about basically FC-NVMe 2. But before we get into that, we'll give you a few introduction slides. But there's a lot of work going on in T11 in enhancing Fibre Channel. And I think after a long time, we really went into the guts of Fibre Channel, sequences and exchanges. And I think the technical minds got together and says, listen, we're going to be really good, but we're going to make it even better, right? And that's what's been happening. And we'll give you a kind of an update on that. So before we get into that, right, the design goals for NVMe, FC-NVMe, right? 3 years ago, even 4 years ago, if you 3 years ago when really NVMe became, we started talking about NVMe in Flash Memory Summit, 3-4 years ago, I think. It was like 500 people in the Flash Memory Summit, right? And now we have like 5,000 people in like 3 or 4 years. Nobody could imagine that Fibre Channel would become such an important transport for NVMe. But the work I think the engineers have done over the last 2-3 years, every single customer we talk to, and we talk about NVMe over fabrics, they are looking at Fibre Channel as a transport. Okay, the design goals were, has to comply with the NVMe-oF spec and keep up with the high performance and the lowest latency possible, in the fabric. One of the biggest design goals was use currently shipping, adapters and switches and optics and cables and the whole infrastructure. So customers who already have invested big bucks, in Fibre Channel infrastructure, right? They can run NVMe traffic over the same infrastructure without having to buy, more hardware. Okay, that was one of the biggest goals, and I think the technical team has succeeded in that very, very well. And then, take advantage of all the services that have already built into Fibre Channel, like name server, zoning, management, which our storage customers are very conversant with. They're experts in all this stuff, and they like it. They like the aspect about how the Fibre Channel fabric can be tightly managed. It's a protocol designed for storage from the grounds up, and you see that when you look at the spec. Again, Fibre Channel, a lot of the protocol actually is done by the chips, right? 80% of the protocol is done by the chips, 20% is done by firmware drivers. But if you look at the latest generation Fibre Channel, equipment, most of the code in the driver is exception handling. More, the I/O, the generic I/O, management is done mostly in firmware and chip. So it's pretty hardware accelerated to begin with, right? And basically with NVMe-oF fabrics, they use FCP protocol, which is already being used for SCSI, moving SCSI traffic. So it's a very mature protocol. It's been there for the last 15-20 years. Well tested. It's on generation 6, and now we are working on Gen 7. So it's got 2 decades of testing and interoperability built into the infrastructure. On the standards update, right? T11 ratified the FC-NVMe standard in 2017, and so it's been a couple of years now almost. So that's great. It works with existing infrastructure, and the performance is is a pretty decent. I have a presentation tomorrow morning early. If you guys keep your beers in control tonight, maybe you can make it tomorrow 8:30 in the morning. I'd love to see you guys. I have actually a few data points on the performance. So we'll give you the performance numbers on Fibre Channel also. Linux is the leading operating system, as you all know, for NVMe over Fabrics, and the other operating systems are in development right now, and we'll share more details on that. But FC-NVMe 2 started work in spring of 18, and Craig is actually the chair of the committee, and he's been leading the industry, on work on FC-NVMe 2, and especially focusing on enhanced error recovery, which he's going to go in excruciating detail today in today's presentation. So once again, the switches are available, and you just have to make sure you're running the right firmware. As you all know, there are really two big switch providers, which I don't have to name, but you just have to make sure you're running the right firmware version on the switches. On the adapter side, again, there are only two, so it's a duopoly here too. But you have to make sure you're running basically, Gen 6 hardware. Switches, Gen 5 and Gen 6 both are supported. And again, the Linux driver is available for download, and on the target side, you have both the user mode and the kernel mode drivers available. Again, VMware is and Microsoft are engaged, but really, Linux is where the software downloads are available. And of course, storage vendors have started to ship already, and we are expecting, by the end of next year, you'll have pretty much all the vendors, having the front end FC-NVMe support in the industry. So with that, I'll hand it over to you, Craig, and then I'll come back in the end and cover some use cases and and give you guys a summary.
So that means tonight you're going to have to control your beer too.
Oh, that's true. It's going to be hard.
All right. So FC-NVMe 2, we're basically almost completed with it. So I wanted to give you an overview of what we're doing with it. So the big thing in FC-NVMe 2 is enhanced error recovery. This allows errors to be recovered, and usually errors are bit errors that result in frame loss, to be recovered in a very fast fashion at the transport layer, not requiring the protocol layer to step in and do recovery. So the question is, why? Why do we need to do this? Well, the dirty little secret is that even for reliable networks, you can still get bit errors. Reliable networks mean that they will not drop frames for reasons of congestion in the network. Doesn't mean you won't get bit errors. And so it's very possible to have multiple bit errors in an hour, depending on the environment and the type of network and the speed you're running at. And of course, you can also have hardware or software errors, which you can't really quantize. You can't say how many you're going to have because those are usually bugs. So what causes these things? We've all heard the cosmic ray thing, and it actually really does happen. Now, of course, we all have ECC memories today, so usually those type of bit errors are detected and either recovered or flagged. Either the machine recovers or it crashes, but you won't have an undetected bit error from that. But not all components in the system, some of the buffers and the intermediate memories may or may not have ECC, so it's still possible for cosmic rays to cause a bit error. We have radiation from the local environment. There's actually been cases where somebody decided to be cheap on their production and use the wrong kind of solder in their chip, and the solder had radioactive lead in it, and it actually started flipping bits. That was I'm sure a really fun diagnostic exercise, yeah. And then RF and power, I'm sure you probably don't have any big units like that in your lab, but anything can start generating power, or not power, noise, and noise can impact memories, and depending on your transmission media, if it's copper, you can actually get noise on the line too. Of course, there's bugs. I probably don't really need to say anything more about that. And the common specified bit error rate for Ethernet and Fibre Channel is 10 to the minus 12th to 10 to the minus 15th, which is the specified rate. Now, the actual rate is much lower than the specified. If you went by the specified rate of current speeds, you could get multiple bit errors per hour, and you usually don't see a lot. You may see a couple per day if you see them at all, but at least the specified rates, you could get quite a few. Whoops, I hit the wrong button. So, how did this work before? There exists in the link layer of most protocols today, or most transports today, something called FEC, which recovers from 90-something% of the errors bit errors you can see. The FECs are mathematical encoding of the bits, which adds some redundancy so that if you have you can recover multiple bit errors in a certain block. But it is still possible for that FEC to be overwhelmed and you go beyond the capacity of the FEC to recover. And in the instance where those happen with current networks or storage networks, the protocols do have protocol level error recovery. Both SCSI and NVMe have mechanisms for doing that. But once you get to a protocol level recovery mechanism, you're entering the world of pain. You're entering 60 seconds longer, because you have to really do a heavy lift. You have to wait for these longish timeouts. You have to re-queue everything. There's a lot of work that has to happen to recover for something. So for FC-NVMe2, our goal for enhanced error recovery was we didn't want the protocol error to see any errors. We didn't want to have to rely on protocol level error recovery. And we wanted to detect these errors very quickly. The error detection that we're going for is around 2 seconds or less, depending on the error condition. So the way they did this, in Fibre Channel, the error recovery takes place on the Fibre Channel frame level. And the recovery mechanism detects missing frames and retransmits them on a very low timeout value. And in order to do this, we defined a series of new Fibre Channel services to do this. And like I said, the goal is that the protocol error doesn't know anything happened. And here's where I dive into details a little bit. So the new stuff we defined in Fibre Channel is something called a basic link service. Basic link service is something which transmits basic symbols, basic signals between this receiver and transmitter. And we defined two new ones, the flush and the red. We also defined a new FC-NVMe command called NVMe-SR, which indicates that we need to retransmit. So flush is used to determine if a command is still active. If a command goes missing, you sound a flush after you determine that it's gone missing. And the flush, if it gets to the other side and the receiver received the flush and didn't receive the command, it knows, the other side knows, hey, something's gone missing here. The sender said, I'm supposed to get something, but I got a flush instead. And you can detect a lost frame that way and not get a retransmitted frame of frame that's already in flight, which is a really bad corner case of error recovery. You don't want to retransmit your data that's already been received. Red is a little bit different. Red is used by the recipient to say, hey, wait a second, I don't think I got everything that you think you sent me. And so the recipient can then tell the sender to start error recovery.
Question.
Yes.
So how is this different from FCP2 had introduced REC SRR?
It's based on that. And I don't have this in this slide deck, but basically the FCP2, the difference between what FCP2 did and what this does is FCP2, because tapes work on a single command per time, if you have multiple commands outstanding, the FCP2 error recovery falls apart. This error recovery is designed to work in an environment where there's multiple commands outstanding, and because Fibre Channel can reorder commands in flight for routing reasons, it also deals with the fact that things can become out of order, and that's why we
So you could send REC for every exchange.
well, that's basically the red is the replacement for the REC. And so, as I mentioned before, the MVSR is the command that says, okay, now we've established that something has gone wrong. Let's start retransmitting things. So, because this is a developers conference, I'm going to punish you with some ladder diagrams. You can't have a developers conference without ladder diagrams. So, we have a read command. The read goes missing. Command is lost. So we have this timeout, which is about 2 seconds, and the timeout says that I send a read command. I haven't seen anything for 2 seconds. What's going on? You send the flush, and on the receiver says, "Wait a second, I got a flush. I didn't get anything." That means that something went wrong, and then the sender can resend because it knows that something went missing. Another possibility is you lose a response to a command. So you get an NVMe command and you get a response back, but the response gets lost. Send the flush again. And this is where the SR comes in. The sender sends the SR to the receiver saying you need to resend that flush. I'm sorry, you need to resend that response. And the response is resent. So, of course, the main thing you're going to be sending for the main packet you'll be sending is data. So we also have to cover data recovery. Same process. A data command goes lost. You get the second data frame because within a certain command exchange, all the frames are in order. If you get the second one, you didn't get the first one, you know something's gone wrong. You send the flush to make sure that nothing's sitting there hiding. And if you get the flush response back, then you know you can send the retry request. And the command is retried. And I'm going to go for this a little bit faster because now we've done it multiple times. Once again, you lose your data frame. You send a flush, and then all the data is retransmitted. Now the red is a little bit of a different example. So we send a write. The first data frame is lost. The second data frame is received, and the target says, hey, wait a second. Once again, I got number 2, and I didn't get number 1. So it sends a red to say something's going wrong, and that triggers the retry. Somebody's trying to talk to you, Rufin. That sends the retry, which triggers the retransmit. Yes?
How much the retry is revealing? How many times retry?
Really what we do is we don't try to continuously retry. If something happens during the retry logic, when it gets lost, then if you get too many errors in that, then we go back and say, okay, there's something wrong with this connection. Let's reset this connection and start again. So we're not trying to cycle down forever and ever and ever and ever. If you have a bad connection, you're continuously losing things, it's not worth trying to retry over and over and over again.
So that would be ABTSR?
Is that?
ABTSR recovery? That one?
No, it's actually a disconnect from the NVMe. Yeah. Okay, so the summary, 2 seconds or less, and this kind of thing is important as the link speeds go up because the perceived number of of possible errors as the link speeds up, even though the actual number of errors is really not anymore, but the perceived numbers can be higher because obviously you have more bits going at any 1 second. So because for that reason, we're also now looking at putting into the SCSI transport as well. And we have a project open called FCP5, which is doing the work to put this into SCSI. Okay, now to a different. Any questions? Any other questions on the error recovery? Okay, going to the roadmap. So the other thing that we work on continuously is bringing out new transport speeds. And this is kind of a summary of what we've done in the past with the different standards, going all the way back to our 1 gig fiber channel. I think that was probably 20 years ago. And I was around for that, which is sad to say. All the way up to our newest speed single lane serial 128 GFC. And we've just completed the 64 GFC PI7, and the PI8, which is 128 FC PI8, is under development. Can't have a fiber channel presentation without the fiber channel roadmap, so we're now down here. I'm hoping to be retired by the time this one comes around. We'll see. And just some abbreviations. Some people get a little bit confused in our nomenclature, but basically, we have these abbreviations, and this is the actual byte rate, and this is the baud rate for those specific abbreviations. Okay, this one's an eye chart. So, as I mentioned, that PI7 was ratified in mid-2018, and as usual, fiber channel, the 64 GF speed is back compatible with the last 2 speeds, so it's back compatible to 32 and 16. That means it's plug and play, and you get speed negotiation depending on what, and it'll negotiate to whatever the common speed is between the 2 links. It also means that the existing cable plant form factors are backwards compatible as well. And for 64 GFC, we kept our usual reach goal, which is 100 meters on OM4, OM5, and 10 kilometers for single mode long distance. And it's probably pretty obvious. 64 GFC doubles the throughput of 32. You would call it 64 for that reason. And the bit error rate stays at the fiber channel standard of 1 to the minus 15th. And this error rate is achieved through forward error correction effect. So a little bit of a dive on FEC. I'm not going to go too much through this because there's a lot of details here. But anyway, FEC now is mandatory for all fiber channel links on S64 GFC. At 32, it was only required for copper. Now for 64, it's required for both copper and optical. And basically, what happens is that it's encoded in something called a Reed-Solomon encoding, and it's coded in a block, and it's re-encoded. The 6256 bit is re-encoded as a 544, 514, which allows for some redundancy in the encoding. And then it's sent in 5140 blocks, and there's a certain error threshold that's allowed in those blocks by the algorithm. If you look at the differences, the uncorrected error rate is 1 to the minus 4th. The correct is 1 to the minus 15th. So you do get quite a bit of a increase there. And for fiber channel is not the only technology. For Ethernet and any other high-speed technologies are using FEC. Otherwise, you couldn't send things reliably at the speeds we're going at today. The other thing that we're working on is a 4-lane version, parallel. We had for 32 GFC, we had a 4-lane version, which was 128, and this will be 256 4-lane. And basically, this is pretty much the same capability as the single lane. And so for 128, single single lane. This is what we're working on right now. And as standard, we're looking at having backward compatibility to 64 and 32. Have the same connectors. Existing cable, though, is probably going to be leaning more to the OM5 instead of OM4. Our goal is 100 meter reach. That's still up for design. We're starting to get to very high speeds here. Looking at 10 kilometers for single mode, and the same BER as well. And there's also a planned 512 version, 4-lane. That one, work hasn't started on that one yet, but that's on the roadmap. Okay. So do I have any questions? Okay. Ruben?
Man, no questions? I think the dessert was too good.
I think so, yeah.
So, yeah, I mean, before I go into this top 6 reasons, I think the reason why the team went ahead and worked on the better error recovery mechanism is because the NVMe stack is kind of brand new stack. And what we found out is that, the protocol layer in the NVMe stack was not as mature as the SCSI layer is, right? So we saw stack teardowns. The multipathing was not as enhanced. So, I mean, overall NVMe stack is still, as you all know, is still being developed and is not as mature as a SCSI stack. So, Fibre Channel decided, listen, we're going to make our transport layer even more robust so that the NVMe stack, gets a better underlying transport, so it doesn't have to do all the error recovery. That was our main motivation of, I think, going ahead and making FC-NVMe 2 and better, error recovery. And now the standards body is going and making those enhancements back to SCSI. So even the SCSI stack is going to become, a little bit more reliable. Okay, so the top 6 reasons why we believe FC-NVMe is going to be a real choice is. The number one is, customers can leverage their existing SAN. I talk to a lot of customers, and customers are buying millions and millions of dollars of Fibre Channel hardware today as we speak, right? And if you're going to buy, spend a couple of $1 million in Gen 6 switches, you're not going to just throw them away, okay? You're going to depreciate them over the next 5 years, and you're going to make sure you use that existing hardware to run this new protocol. So I think that's one of the reasons why FC-NVMe is going to have a place in the enterprise. Again, the beauty is they can run both NVMe traffic as well as standard SCSI traffic on the same port, even on the same port. So you don't even have to go and dedicate your Fibre Channel ports for NVMe. You can run basically both protocols on the same port. The name server, name server and discovery, the features that are kind of we take them for granted in Fibre Channel, right? Storage guys really like that. The fact that it's a fabric, everybody knows when they come in the fabric, when they go out of the fabric, everything is managed in zones. They can kind of create these fault domains and provide that SLA to their applications. Zoning and security I talked about. Again, the fifth point is the qualification. Now, Fibre Channel infrastructure, right? When you buy a Fibre Channel storage array today, customers are well educated and well informed that they have to make sure that proper interoperability and qualification has taken place. And I mean, I work for Hewlett-Packard, and we do spend quite a bit of money in interoperability and qualification, and we make sure we work with our partners to give our customers a fully qualified solution that they can, comfortably deploy. And the reason why Fibre Channel continues to remain popular is the fact that storage admins can play golf on Saturdays and not have to worry about the pager, ringing, right? And again, I think with FC-NVMe 2, the engineers have done a fantastic job in making the transport even more robust. So again, this is the last slide, actually second last, one more slide after this. It's wicked fast. I live in Boston, so I have to use the word wicked. And like I said, 20 plus years of protocol, runway, and it has a brand. It has a trust. Fibre Channel has a trust. You can't just take away. This is the last slide. We just published a new solution guide for 2019. Actually, I'm the editor. And I actually wrote an article also on FC-NVMe 2 in this guide. So you can download this. It's excellent bathroom reading.
And it's mostly correct.
It's mostly correct. The bit error rate algorithms have run through the solution guide. But it's an 18-page, 19-page guide. It's got quite a bit of technical content in there also, so I think engineers would love to read it. And it also has a roadmap, FC roadmap. It also has some other interesting articles. So thank you all for attending our session, and we are here for questions now. Also, you can catch us at the reception in the evening. So we have quite a bit of time now, right? 20 minutes? So questions? Please.
Do you have any benchmarks to show or share anecdotally even between 16 gig fiber channel, let's say, single port?
About performance?
Benchmark, yeah, performance.
We always say like 2x, right? In performance, right? Speed bump is 2x in performance. You go from 16 to 32, you get double the bandwidth.
Are you talking about performance between the new speeds or for FC-NVMe?
Well, if I have a host that I'm running 16 gig fiber channeling through a single port, and I have a storage subsystem that it's already running PCIe, NVMe interconnection for the flash modules, right? Mm-hmm. And I switch that port from 16 gig fiber channel
to 16 gig NVMe.
Exactly.
Okay, so I have the numbers for tomorrow's presentation, but I'll give you in a preview right now. If you just switch the protocol, from Fibre Channel to NVMe, from SCSI to NVMe, running on the same exact transport, we are seeing about 15 to 20% improvement in performance.
I'm sorry, what was the number?
15 to 20% improvement in performance.
Thank you.
Just pure protocol, no hardware changes, no software changes.
Dennis Norton out of Martech essentially just that last year in the middle of the year using NetApp storage and Brocade 6510. All he did was drop in the NVMe driver onto the host, and his experience was even better.
40%, I think. In Demartech, Dennis, I know Dennis very well. I think his paper said 40%, but that's a real target. When I did my performance comparison, I did use the soft target assemblies, right? Because I don't know what additional performance tweaks they did, when they moved from SCSI to NVMe in that particular test case. But I'm just saying from a protocol perspective, right? No additional tweaks in the hardware or software. You're seeing about 15 to 20% improvements. If you do further tweaks, you can get 40%. In fact, you can get even more potentially.
What's the scalability of Fibre Channel? Like how many?
Oh, it's huge. I have seen sites that I cannot name with 20, 30,000 port SANs. Huge.
In your benchmarks, how many Q pairs did you have? IO Q pairs?
I think it was like 126, but I have to confirm that.
You can max out the line speed through a traditional FCP, right? So the 15% performance, can you explain that? Is that more IOPS? Is it lower latency? What's the
When we do a performance benchmark, generally we do one server, FIO, 4K reads writes. So we don't try to saturate, the line. Any other questions, guys? Well, thank you.